In the heart of New York City, a gleaming skyscraper stood tall. It was a symbol of modern design and bold engineering. People walked below it every day. They worked inside its offices, unaware of a secret. This building, the Citicorp Center, was hiding a dangerous flaw. It was a mistake so serious that a strong storm could have brought the entire 59-story structure crashing down. The story of this building is not just about steel and glass. It is a story about a hidden weakness, a brave engineer, and a race against time to prevent a catastrophe that could have been one of the worst in the city's history. It shows us that even the most impressive structures can have hidden faults. The problem was born from the building's most celebrated feature. The designers wanted to create something new, something that had never been seen before. They lifted the entire skyscraper off the ground, placing it on 4 massive columns. This created an open space below, a public plaza for everyone to enjoy. But this innovative idea came with a risk. The design was tested and approved, and construction went ahead. The building was completed in 1977, a proud addition to the Manhattan skyline. For a year, it stood without incident. Nobody knew that a simple change made during construction had turned its unique strength into a critical vulnerability, waiting for the right kind of wind to reveal its deadly secret. This is a tale that reminds us that engineering is a human activity. Humans make mistakes. But what happens after a mistake is discovered is what truly matters. In this case, the chief structural engineer, a man named William Le Mesurier, found the error himself. He was the one who designed the support system. He was the one who had to face the terrifying reality of his own miscalculation. The weight of this knowledge must have been immense. He held the safety of thousands of people in his hands. His professional reputation, his career, and the lives of countless New Yorkers were all on the line, balanced precariously on a flawed connection deep within the tower's steel skeleton. The drama unfolded in secret, hidden from the public eye. While the city slept, a team of workers moved silently through the building's empty floors. They worked through the night, cutting into the structure and welding new steel plates to strengthen it. It was a clandestine operation, a heroic effort to correct a mistake before nature could exploit it. The story of the Citicorp Center is a thriller set not in a spy movie, but in the world of blueprints, wind tunnels, and structural analysis. It serves as a powerful lesson about responsibility, ethics, and the courage to do the right thing, no matter the personal cost. It is a story of how disaster was quietly averted by one person's integrity. The Citicorp Center was born from a unique challenge. A church, St. Peter's Lutheran Church, occupied a corner of the land where the tower was to be built. The church leaders agreed to sell the land, but with one important condition. They wanted a new church to be built in the same spot, as a separate and freestanding building. This meant the skyscraper could not have columns at its corners like a normal building. The architects and engineers had to find a creative solution. They had to build a massive tower that seemed to float above the new church. This problem led to a design that was both revolutionary and visually stunning, capturing the imagination of the public and the architectural world alike. The solution proposed by the engineering team, led by William Le Mesurier, was daring. Instead of placing columns at the 4 corners, they decided to place 4 huge columns at the center of each side of the building. These massive stilts would lift the entire 59-story structure 9 stories into the air. This design choice created a large open plaza underneath the building and allowed the new St. Peter's Church to be constructed on its corner. The tower seemed to hover over the street, a giant of concrete and steel supported on legs. It was an engineering marvel, a testament to what could be achieved when faced with a difficult constraint. These enormous columns, each 9 stories tall, carried the immense weight of the building. The load from the entire structure had to be transferred from the edges of the building down to these central supports. To do this, the engineers designed a system of giant V-shaped braces, known as chevrons. These braces were stacked on top of each other, forming a visible pattern on the building's exterior. They acted like a giant skeleton, collecting the weight from each floor and channeling it downwards and inwards to the 4 massive columns. This system was not only functional, but also gave the building its distinctive look. It was a design that was both honest and elegant, showing its structure on the outside. When the Citicorp Center was finished in 1977, it was celebrated for its innovation. It was a skyscraper that did more than just reach for the sky. It engaged with the city at street level. The open plaza became a new public space, and the building itself became an instant landmark. The design was praised for its intelligence and beauty. It solved a complex problem with a solution that was both practical and artistic. No one suspected that the very same design that made the building famous also contained a hidden flaw. The building stood as a proud example of modern engineering, while its greatest weakness remained undiscovered, deep within its steel joints. The core of the Citicorp Center's structural integrity relied on a brilliant system of stacked V-shaped braces. These were not just decorative elements on the building's face, they were the primary load-bearing components. Imagine a giant hollow tube made of steel and glass. The chevron braces acted as the internal skeleton for this tube. Each V-shaped brace was designed to collect the immense weight from the floors above it. They took these vertical forces and redirected them diagonally, channeling them towards the four massive columns that supported the entire structure. This was a clever way to move the building's weight from its perimeter to its center, a necessary step because of the column's unusual placement. These braces were designed to handle the two main forces that act on any skyscraper: gravity and wind. Gravity constantly pulls the building downwards, and the chevron system was more than strong enough to handle this constant load. The second force, wind, is more complex. Wind pushes against the side of a building, trying to make it sway or even topple over. The engineers designed the braces to act as a rigid frame against this push. When wind blew directly against one of the flat sides of the building, what engineers call a perpendicular wind, the braces on that side would be compressed, while the braces on the opposite side would be stretched. The system was designed to handle these forces efficiently. During the design phase, the engineers calculated the strength needed for every part of the structure. They focused on how the braces would perform under the stress of these perpendicular winds, which were considered the most powerful force the building would have to face. For these connections, the engineers specified that the steel pieces should be welded together. Welded joints are incredibly strong and rigid, creating a single, solid piece of steel that can resist immense force. This was the standard and correct approach for designing a building to withstand the powerful gales that can sweep through a city like New York. The welded joints were meant to ensure the building would stand firm against hurricane-force winds. However, a small but critical change was made during the construction process. The building contractor suggested that using high-strength bolted joints instead of welded joints for the chevron braces would be faster and cheaper. The engineering firm approved this change, believing that the bolted joints would be strong enough. This decision was based on the calculations for perpendicular winds. Bolts are very strong when a force pulls on them, but they are not as rigid as welds when the force comes from a different angle. This seemingly minor substitution, swapping welds for bolts, was the key to the problem. It created a hidden weakness that no one noticed until it was almost too late. The engineers had designed the Citicorp Center's support system to be strong against winds that hit the building's flat faces directly. This is the most common way to test a building's strength. Think of the wind pushing straight against a wall. The chevron braces were designed to transfer this force safely to the ground. The calculations showed that the bolted joints, which had replaced the original welded design, were strong enough for this kind of stress. Everyone involved in the project, from the engineers to the builders, believed the building was safe. They had followed the standard practices and building codes of the time, which focused primarily on these perpendicular wind forces. The problem lay with a different kind of wind, one that the original calculations had overlooked. This was a quartering wind, a wind that strikes the building at a 45-degree angle, hitting two sides at once. When a wind hits a corner, its effect on the structure is very different. Instead of some braces being compressed and others being stretched, a quartering wind puts almost all the diagonal braces on all four sides of the building under tension simultaneously. This meant that the force on each individual joint was much higher than anyone had anticipated. The bolts in every single one of the 200 chevron joints were suddenly put under immense strain. This is where the change from welded joints to bolted joints became a critical flaw. Welded joints fuse the steel plates together, making them act as one solid piece. They are incredibly strong under all kinds of forces. Bolted joints, however, are different. They work by clamping steel plates together. While they are strong when pulled directly apart, they are much weaker when the force tries to shear them or pull them in multiple directions at once. The quartering winds created exactly this kind of complex stress on the bolts. The force on the bolts was increased by 40% under these specific wind conditions. This was a massive increase that the original design did not account for. Even more alarmingly, the structure was now significantly more vulnerable to strong storms. The original design, with welded joints, was strong enough to withstand what engineers call a 100-year storm, a storm so severe it is only expected to happen once a century. But with the weaker bolted joints, the analysis showed a terrifying new reality. A storm that was statistically likely to happen every 16 years would be strong enough to cause the bolts on some joints to fail. If these bolts failed, the load would shift to other joints, causing them to fail in a chain reaction. The entire skyscraper could collapse in a matter of hours, a catastrophic failure triggered by a specific type of wind. The discovery of this terrible flaw did not come from a senior engineer or a building inspector. It began with a simple question from an undergraduate architecture student. In 1978, a year after the building was completed, a student from New Jersey named Diane Hartley was writing her thesis on the Citicorp Center. As part of her research, she called William Lemesurier's office with some technical questions about the design. She had been told by one of her professors that the columns were unusually placed in the center of the building's sides, not at the corners. She wanted to understand how the building handled wind loads, and she specifically asked about the forces from quartering winds. Lemesurier was not in the office that day, but a junior engineer answered her questions based on the official design documents. The student was persistent. She followed up, and her questions were eventually passed on to Lemesurier himself. Lemesurier, confident in his design, patiently explained that the building was perfectly safe. He described how the structure was designed to handle perpendicular winds, the strongest forces it was expected to face. He assured her that his team had done all the necessary calculations and that the building was sound. He likely thought of it as a routine inquiry, a simple chance to educate a curious student about his celebrated work. However, the student's question about quartering winds stuck in Lemesurier's mind. He had not personally analyzed the effect of these diagonal winds on the bolted joints. The building codes at the time did not require it. But driven by a sense of professional curiosity and responsibility, he decided to double-check the calculations himself. He went back to his office and ran the numbers, this time specifically modeling the stress on the bolted joints from a 45-degree wind. He wanted to prove to himself that the student's concern was unfounded and that his design was as robust as he believed it to be. It was a decision that would change everything. As he worked through the complex equations, a feeling of dread began to grow. The numbers on the page told a horrifying story. The student was right to be concerned. The quartering winds put a much greater strain on the bolted joints than anyone had realized, a 40% increase in stress. Then, Lemesurier remembered another critical detail. The building also had a tuned mass damper, a 400-ton block of concrete on the roof designed to reduce the building's sway. This device needed electricity to work. In a hurricane, the power would likely fail, rendering the damper useless. This would increase the stress on the joints by another 40%. The combined effect was a potential 160% overload on the bolts. The building was dangerously unsafe. William Lemesurier was now faced with a reality far worse than any engineer's nightmare. His calculations were undeniable. His celebrated skyscraper, a landmark on the New York City skyline, was a ticking time bomb. According to his analysis, a storm with wind speeds of just 70 miles per hour, if it hit the building at the right angle, could start a catastrophic failure. Such a storm was not a rare 1,000-year event. It was a storm that had a statistical probability of hitting New York City once every 16 years. The city was currently in the middle of hurricane season. The risk was not theoretical or distant. It was immediate and terrifyingly real. The weight of this discovery was immense. Lemesurier had to confront his own mistake. He had approved the switch from welded joints to bolted joints, a decision made to save time and money. He had not considered the effects of quartering winds on these bolts. Now the lives of thousands of people in the building and the surrounding city blocks rested on his shoulders. He had several options. He could keep quiet and hope that a severe storm would never hit. Revealing the flaw would surely ruin his career, destroy his reputation, and expose his firm to massive lawsuits. The temptation to hide the problem must have been enormous. Instead of hiding, Le Mesurier chose the path of professional integrity and moral courage. He knew he could not live with the risk, no matter how small the chance of it happening seemed. He had a duty to protect the public, an ethical obligation that is at the very core of the engineering profession. He contacted his insurance company to inform them of the potential for a massive claim. Then, he prepared a detailed report of his findings. He knew he had to inform the building's owner, Citicorp, and the city authorities. He was about to admit to a mistake that could have unimaginable consequences, both for the city and for himself. He flew to New York to meet with the executives at Citicorp. In a calm and professional manner, he laid out the facts. He explained the nature of the flaw, the precise level of risk, and the conditions that could lead to a disaster. He did not make excuses or try to shift the blame. He presented the problem clearly and also came prepared with a solution. He had already designed a repair plan, a way to strengthen the 200 bolted joints by welding heavy steel plates over them. He took full responsibility for the error and outlined a clear path to make the building safe. It was an act of incredible professional bravery. With Citicorp's leadership and city officials now aware of the danger, a plan was immediately put into action. The most critical challenge was to carry out the repairs without causing a public panic. If news of the building's instability leaked out, it could create chaos in one of the world's busiest cities. The decision was made to perform the work in absolute secrecy. A team of welders was assembled, and a cover story was created. The public was told that routine maintenance and inspection work was being done on the building's structural system. This allowed the workers and materials to move in and out of the building without raising suspicion. The repair operation was a race against the clock and the weather. It was the height of the Atlantic hurricane season, and every day brought the risk of a storm. The work could only be done at night, after the thousands of office workers had gone home. From 8 p.m. to 4 a.m., the welders would move into the empty office spaces. They would remove sections of the walls to access the steel skeleton underneath. Then, they would carefully weld 2-inch thick steel plates over each of the 200 bolted joints, reinforcing them to withstand the forces they were never designed to handle. It was difficult, noisy, and dangerous work carried out in the dead of night. The logistics of the operation were incredibly complex. Le Mesurier and a team of engineers stayed on site, overseeing every step of the process. They worked with meteorologists who provided constant weather updates, giving them a 5-day forecast for the Atlantic. A detailed emergency evacuation plan was created in secret. This plan, developed with the Red Cross and local police, would be triggered if a hurricane was forecast to head towards New York. It involved evacuating the Citicorp Center and a 10-block radius around it, a massive undertaking that everyone hoped they would never have to execute. The tension was palpable as the team worked through the summer nights, strengthening the building one joint at a time. For weeks, the secret drama played out high above the sleeping city. During the day, the building operated as usual. Office workers typed at their desks, made phone calls, and held meetings, completely unaware of the frantic life-or-death repairs that had taken place just hours before. The welders and engineers worked tirelessly, their progress hidden behind temporary walls. They were slowly but surely turning a critically flawed structure into a safe one. The secrecy held, the public remained unaware, and the steel plates were welded one by one, each spark in the night a small victory against a potential disaster. As the secret repair work continued through August and into September of 1978, the team on the ground kept a constant, anxious watch on the weather. The greatest fear was a major hurricane moving up the East Coast and setting its sights on New York City. Halfway through the repairs, that fear almost became a reality. A powerful storm, Hurricane Ella, formed in the Atlantic and began to track westward. For several days it grew in strength and moved on a path that could bring it directly to the city. For Le Mesurier and the others involved in the secret operation, this was the moment they had been dreading. The atmosphere inside the emergency command center became incredibly tense. Meteorologists were providing hourly updates on the hurricane's position and predicted path. The evacuation plan for the 10-block area around Citicorp Center was ready to be activated. Le Mesurier was on the phone with officials, preparing to make the call that would trigger a massive and unprecedented evacuation of a part of Manhattan. The fate of the building and the safety of the surrounding neighborhood hung in the balance, dependent on the unpredictable path of a swirling storm. The welders worked faster, knowing that their time might be running out. Then, just as it seemed a catastrophe was unavoidable, fate intervened. As Hurricane Ella approached the coast, it suddenly and unexpectedly changed course. It turned northward and veered out into the open Atlantic Ocean, away from land. The storm that had threatened to expose the building's fatal flaw and cause a disaster of unimaginable proportions dissipated harmlessly at sea. A collective sigh of relief went through the small group of people who knew the secret. They had been spared. The hurricane that never came gave them the precious time they needed to finish the repairs and secure the building. By the end of September, the work was complete. All 200 bolted joints had been reinforced with heavy welded steel plates. The skyscraper's skeleton was now stronger than it had ever been, even stronger than in the original design. The secret had been kept, a panic had been averted, and the building was finally safe. The crisis was over. The story of the near disaster remained a closely guarded secret among the handful of engineers, executives, and city officials who had lived through it. For nearly 2 decades, the public would remain completely unaware of how close New York City had come to a major tragedy. The story of the Citicorp Center crisis was finally made public in a 1995 article in the New Yorker magazine. It revealed to the world the incredible drama that had unfolded in secret 17 years earlier. Instead of facing ruin and disgrace, William Le Mesurier was hailed as a hero. His actions became a celebrated case study in engineering ethics, taught in universities around the world. He demonstrated that the highest duty of an engineer is to protect the public's safety, even if it means admitting to a serious personal mistake. His courage to speak up, take responsibility, and act decisively saved countless lives and prevented a devastating disaster. The Citicorp Center affair provides several powerful lessons. First, it highlights the importance of thoroughness in engineering design. The initial flaw was created by overlooking the effect of quartering winds and by approving a seemingly minor change in construction materials without fully re-evaluating the entire system. It shows that even small changes can have large, unforeseen consequences. It underscores the need for engineers to question assumptions, check every detail, and consider all possibilities, not just the ones required by the building codes of the day. The codes, after all, represent the minimum standard for safety, not the highest. Furthermore, the story is a profound example of ethical responsibility. When faced with a terrible choice between protecting his reputation and protecting the public, Le Mesurier chose the public. He did not hide his mistake or hope for the best. He confronted the problem head-on, with honesty and integrity. This moral courage is perhaps the most important quality an engineer can possess. Structures of steel and concrete are ultimately built on a foundation of trust. People trust that engineers have done their work correctly and diligently. Le Mesurier's actions reinforced that trust by showing what it means to be truly accountable. Today, the Citicorp Center, now known as the Citigroup Center, still stands tall and proud in the Manhattan skyline. It is one of the safest buildings in the world, its structure made robust by the secret repairs performed so long ago. But its true legacy is not just in its physical strength, but in the story it represents. It is a permanent reminder that engineering is a human endeavor, and with that comes the possibility of error. More importantly, it is a testament to the fact that integrity, honesty, and the courage to do the right thing are the most critical components in any great structure. It is a lesson written not just in textbooks, but in the steel heart of a skyscraper.